Now we have here the elastic band theory. Before we move on to the double integration, let's first derive this formula that is used in that method. Now we have here a simple wheel with its end supported by two joints A and B with a non-uniform bearing load here. Now in theory, the elastic curve should look like something like this. If we took a length of x here, we can refer that we can section out a part. Let's say this is the x and this is also the x. If we zoom in on the figure, we will have something like this. Now, in this figure, we have what we call the neutral axis. In the neutral axis, basically it's just the axis from which the loads or the forces becomes a transition from tension to compression or compression to tension. Now let's say that in the neutral axis, we have a length of dx. And above the neutral axis or the dx, we have a length of ds. Now, let's say that we bend the figure. This is before the curve or before bending, and this is after bending. It look like something like this. Yeah. Now, we have here again the neutral axis. It has a length of dx, but our ds changed in value. Therefore, it is now called ds prime. As you can see, there's a curvature in the figure. If we extend these lines outwards, where it intersects, we have what we call point O with an angle of theta. Now, this is a section of a circle, which means this is an arc. The formula for an arc, as we remember, is S is equal to radius multiplied by theta. Let's say that the distance from ds and dx is y. Therefore, ds and dx also have a distance of y. But let's say that the radius from point O to dx is rho. It's rho. Now, if we recall the formula for strain, strain is equal to deformation all over original length, which is also equal to L prime minus L all over L, the new length minus original length over original length. Now, in this figure, we know that ds prime is equal to L prime, and ds, which is also equal to dx in this figure, is equal to the original length. Now, another formula for let's try to integrate ds prime in terms of the arc. That is ds prime. So what's the formula for ds prime? ds prime is basically equal to the radius, which is rho minus y. So rho minus y multiplied by the angle or the angle theta. Now, ds is equal to dx. Therefore, ds in this is equals to rho multiplied by theta. Rho theta. Now, if we try to combine all these terms, we will get that strain is equal to L prime, so rho minus y theta minus rho theta all over rho theta. Let's cancel out the rho's and cancel this out because rho minus rho is 0. Therefore, our strain is equal to negative y all over rho. Now let's move on to another problem or another equation. Let's say we know that let's assume that this bending occurs at Hooke's law, so the proportional limit. Hooke's law is then applied. Hooke's law is, let's transfer here. Hooke's law is just the stress, or in this case, the bending stress is equal to strain all over the modulus of elasticity. Now let's combine these two terms in terms of E, or in terms of the strain. So strain is equals to bending stress all over E. equated here. Therefore, the bending stress all over E is equal to negative y rho. Now, let's call this equation 1. Now, another thing that we can do is create a cutout here. Let's say that we cut out this bell curve. If we cut out this figure, we will see that this is the cutout, this is the cross-sectional cutout of this figure. We see that it has a bending stress, and here is the neutral axis. Let's take an element in this cross-section. Let's say I take an element here. Now this element has an area of dA. And we know, as I said, this is in compression and this is in tension. Therefore, we have a force going here and a force going here. There are couple moments. Therefore, this is the direction of our moment. Therefore, we have a changing moment here, dm. The distance of dA from the neutral axis, let's call that y. And we have another force here. Let's call it the F. Now, in order to, let's try to create a formula based on Tm and the stress. So we know that stress is equal to, so negative dF because it's going to the left. dF all over dA. And we know that moment or changing moment is equal to the distance or y multiplied by the force dF. Yeah, there we go. Now let's combine this in terms of dF. We know that dF here, so this is also equal to change in dF here. dF is equal to bending stress multiplied by the change in area negative. Let's combine these two terms here. So our two terms now here is change in moment is equal to y multiplied by, or it's negative, dA. Now, we will multiply this side by y over y. Y over y is just equal to 1. So we multiply it by 1. In order to get a specific equation, we now therefore get change in m is equals to negative rho b all over y times dA multiplied by y squared. Let's get the integral of this problem. Now, if you can see here, it's a familiar equation because this is equal to the second moment of inertia. Therefore, here the integral of change in m is equal to negative rho b over y multiplied by I. Now, this is our equation 2. We need to combine equation 1 and equation 2 in terms of the bending stress. Therefore, let's try to change equation 2. So, m y all over I is equal to change in the negative. The change will be here. Let's put negative m y all over I is equal over E is equal to negative y all over rho. Now, let's cancel out the negatives, y's, and you will get an equation of 1 over rho is equal to m-I-E. Now, this is actually our final equation. But we can simplify 1 over rho because 1 over rho is equal to 1 over r. And in calculus, we can recall that r is equal to 1 minus dy over dx raised to 2 raised to 3 over 2 all over the second derivative, which is d squared y all over dx squared. We just get the reciprocal of this problem, and we will get that 1 over r is equal to d squared y all over dx all over dx squared all over 1 minus dy dx squared raised to 3 over 2. Now what's the value of dy over dx? If we go back to this problem and we zoom in here, we can see that the curve here has dx and dy, and it has a slope of theta. Now, in theory, the slope here is very minimal, that to the point that it's considered as negligible and equal to 0. Therefore, in this equation, dy over dx is equals to 0. Therefore, this whole denominator part will be equal to 1. Therefore, 1 over r or 1 over rho, as we have established, is equals to d squared y all over dx squared or y double prime. Let's just substitute this value here, and we get our final equation of y double prime is equals to m I d. Just rearrange this to get this equation. We have here another method, the double integration method. What charts are the first presenter? The problem they solve is very similar to this, but the only difference is that our distributed load is rectangular in shape, and the first problem was triangular in shape. Now we have here two reactions, RA, RB, and moment here at point A. But as you can see, there's no vertical reaction because, or horizontal reaction because our loads are only vertical. Anyway, now first thing to do is to find an origin of the point, or we're going to cut out the sections. A rule of thumb is that in the double integration method, try to avoid cutting where the cut encompasses the distributed load, because there is a method that you can use when we cut it from A, but since this is double integration method, let's make it easier and cut it at B. Now let's go and cut it here. Now this is our x, and this will be our cut, section E. Now, the first thing to do is establish that our derived formula, which is m is equals to ei y double prime. Now, if you try to solve the moment, we know that ei, the y double prime, is equal to, let's first solve this, rb, with a distance of x, rb, x. Let's say that this is going in counterclockwise direction, that's positive. Rbx, so minus 50 kilonewton multiplied by its distance, so x minus 1. X minus 1. Let's try to move the units first to just make the right easier. So x minus 1. So minus the distributed load of 20 kilonewton meter, so 20 kilonewton meter multiplied by the procedure, so x minus 2, and its distance of x minus 2. Since it's rectangular load, our distance is its length all over 2. Now we just try to first let's integrate. Let's integrate first in our own integration. So first integration of the problem. Now ei y prime is equal to rbx all over rbx squared over 2 minus 50. So I'm just going to simplify it to make it faster. 25. Since x minus 1, the integration of this is x minus 1 squared over 2. So x minus 1 squared minus 20 divided by 2, so 10 all over x minus 2, so they're the same. That's therefore x, we integrate them to become raised to the third power, then all over 3 plus our constant c sub 1. So let's say this is our equation 1. At 1. Let's try to integrate it further because the method is called double integration. Integrate. Therefore, EI y is equal to RBX squared. So RBX cubed all over 3 times 2, 6 minus 25 all over 3 multiplied by x minus 1 cubed minus 3, 4, 12, so 10 all over 12 multiplied by x minus 2 raised to 4 plus C1x plus our second constant 2. Now we have solved this, let's call it equation 2. Let's solve for the boundary conditions using the boundary conditions. So let's say at joint B. So at joint B, we know that joint B is our origin. So let's say it's equal to x and its deflection is equal to y. Therefore, if we use this solution, we'll get that EIY is equal to 0 and equal to RBX cubed. So x is equal to 0, cancel. 0 minus 1 is cancelled. 0 minus 2 cancelled. C1x 0 plus C2. The only remaining variable is C2. Therefore, C2 is equal to 0. Now let's move on at joint A. At joint A, we know that at joint A, our x is equal to the maximum. So x is equal to 5. And since the deflection here is also equal to 0, so y is equal to 0. Now let's use equation 2 again. So EIY is equal to 0. So 0 is equal to, now we have here RB 5 raised to 3. So RB with 5 raised to 3 all over 6 minus 25. So 5 minus 1 is 4. So 25 all over 3 divided by 4 raised to 3 or 3? 3. 2, 3 minus 10 over 12 by x minus 2 raised to 4 or 3 raised to 4. 3 raised to 4 plus C1x. So plus C1x plus C sub 2 which is equal to 0. So it's cancelled out. 0. Now let's try to simplify the problem. So RB0 is equal to RB RB 5 raised to 3, so 125 all over 6. And let's combine these two terms, which is equal to 3,605. 3,605 all over 6. 6 plus C1x. Now, let's call it equation 3. Equation 3. We can solve for this because we still have two unknowns and we need two equations to find two unknowns. So let's try to solve, let's try to create another equation. Sorry. C1x 5 pala to. Thank you for that. So 5. Yan. So 5. Now let's actually simplify this equation 3. So if we simplify this, we parenthesis divided by 5, 0 is equal to 25 all over 6 RB minus 721 all over 6 plus C1. Now this is our equation 3. Equation 3. Now let's stay at joint A. In theory, this is a fixed hinge. Therefore, our deflection here, or our elastic curve should be something like this. Now, the slope at this joint A is equal to 0. Slope will be equal to 0 the slope will be equal to 0. Therefore, we can assume at joint A, y prime is also called the slope, is equal to 0 at x is equals to 5. Therefore, we can use now equation 1 in order to solve for another, in order to create another equation. Now, here, again, y prime is equal to 0, so 0. So 0 is equal to RB squared, so 5 RB 5 squared 25 all over 2 minus 25 x minus 1 is 4 squared minus n multiplied by x minus 2, so 3 cube all over 3 plus c sub 1. Now let's just try to combine items. So RB 25 all over 2 minus, solve for this,
490.
490 sakto. 490 plus c sub 1. Now this is our equation 4. Equation 4. Now let's combine equation 3 and equation 4. We can solve for C1 here. So I'm just going to rearrange this. So let's say that equation 3, so C1 is equal to, so negative, this will be negative 25 all over 6 RB minus, or plus 721 all over 6. And equation 4 will be equal to C1 is equal to negative 25 over 2, negative 25 all over 2 RB by plus 490. 490. Ano sulat ko dito? Parang balik. Tawa na pala. So therefore, let's try to solve for RB. So let's have a negative value here. Therefore, C1 minus C1 is 0 is equal to negative 25 over 6 minus negative 25 over 2 is 2,219
all over 6.
all over 6. Ano sign?
Positive.
So positive. Therefore, we can solve for the reaction of B. So the reaction at B is equal to negative
Positive.
Negative ano ito?
Positive.
2,
Positive 2,219.
2219 all over 6.
50.
O, 50 ba?
50. 50.
So 50 pala. 50 all over 25, 3. So the reaction of B is equal to
44.38 kilonewtons.
positive, negative.
Positive.
Negative R. This should be negative. Kasi mas malaki ito eh. Tama lang, negative ito. Therefore, negative, positive, positive. Sorry for that. This will be negative, negative. Yan. So it's positive, positive, 48 for 38 kilonewtons. So this is our RB. Now, the last one is RA. We can just simply substitute RB to the equation, or actually, we can just, since we have RB, we can solve for the entire equation using the boundary conditions. Or boundary conditions, sorry, for the equilibrium equation. Dito na lang. So, in the equilibrium equation, we know that the summation of forces, summation of F of B going positive upwards is equal to 0. Therefore, 0 is equal to RB going upwards of 44.38 kilonewtons minus 50 kilonewtons minus 20 kilonewton per meter multiplied by its distance, which is 3 meters. So 3 meters, cancel, plus RA. Therefore, our equation will be RA is equal to negative
65.62 kilonewtons.
62 kilonewtons. 62 kilonewtons. Therefore, if we just transpose the problem, we find that RA is equals to 65.62 kilonewtons. Now, for the moment naman, sorry din pumasok po kasi kaya kinat. Anyway, for the moment, since di naman natin kailangan, bupreso nyo naman. Now, for the moment, it's just simple again, it's just simple equilibrium. Let's say that we're going to be creating summation of moment at joint A. So I'm gonna call this big letter A as, there's no any confusion, A. Yan. Let's say at moment, summation of moments at AA going to the clockwise direction is equal to 0. So therefore, the forces here will be equal to MA, so it's going to the left. So 0 is equal to MA going to the clockwise, so it's negative MA plus the distributed load. So let's add, it's already, so 60 kilonewton times its distance of so 1.5 meters plus 50 kilonewton multiplied by 134 meters minus RB, which is 44.38 kilonewtons times 5 meters. Now let's just solve for this equation. We will get that MA is equal to
68.10 kilonewtons times
meter. Right. So this will be our final answers. MA, reaction at B, and reaction A.